Hello everyone. Welcome to HYPRES' presentation of our Navy Phase 2 SPIR project on digital RF beamforming. My name is Deep Narayan Gupta. I'm the principal investigator and I also run HYPRES' Digital RF Circuits and Systems division, which has always been the largest business division and currently conducts over 90% of the company's business. In HYPRES' digital RF technology, radio frequency signals ranging from below 100 Hz to above 100 GHz are directly converted to the digital domain, where the rest of the signal processing is performed. HYPRES started its Advanced Digital RF Receiver, or ADR, journey over 15 years ago, following an $8 million SPIR Phase 2 contract funded by the OSD through the Office of Naval Research. Since then, the technology has spiraled up to its 5th generation. These are modular multifunction receivers, the functionality of which is determined by superconductor microelectronics complemented by state-of-the-art FPGA technology. Superconductor analog to digital converters, or ADCs, spearhead the ADR systems. They use ultra-short 2 picosecond wide single flux quantum pulses to sample the analog input signals up to very high frequencies and perform digital processing with the same clock. The project we'll discuss today extend the digital processing with superconductor microelectronics. Third generation ADR systems launched over 10 years ago are still in use, and one of them has just had yet another modular upgrade. The 4th generation systems completed testing on platforms for sea, air, and land this year and are now at Technology Readiness Level 7. It's part of Army's Critical Sensing Technology Generation 4, or CSTG4 program. We are happy to announce that the 5th generation prototype has been delivered under another ONR Phase 2 program for use in different naval facilities last month. Radio frequency reception is not the only application. HYPRES is pursuing also imaging applications, where the digital RF technology complements cryogenic sensing. The objective of the present SPIR project is to address the need for spatial filtering over a wide frequency range. Our solution to this well-known problem of locating and tracking RF emitters is to perform precise digital true time delay after digitizing the output from multiple antennas. The concept, which I'll show in the next couple of charts, is well known. The method of measuring spatial dimensions using time delays removes frequency dependence. Therefore, digital RF beamforming is inherently very wideband. It takes full advantage of superconductor ADCs and very low power digital signal processing at 40 to 60 GHz clock frequencies residing on the same integrated circuit. The goal is to enable formation of multiple simultaneous receive beams using the same array of N antennas. The incident signal is digitized directly behind each antenna element. The advantage in converting to digital is that each signal can be copied as many times as necessary without suffering any loss of power or fidelity. Digital time delays are next applied on each set of copies and summed to form individual beams. For example, for the first emitter, we apply delays tau sub 1, tau sub 1, etc. up to tau sub 1n and sum them. For the second, we take another set of copies from the same n ADCs and apply a second set of delays, tau sub 1, tau sub 2, etc. up to tau sub 2n. By modular expansion of processing blocks, we can scale up this digital RF beamforming scheme to any number of antenna elements and any number of simultaneous receive beams. For proper beam shaping, we have designed delay multiply units so that each delayed component can be multiplied by weights. The processing is summarized here. Analog output of each N antenna elements are directly digitized at RF, split into N digital copies for formation of N beams. Each copy is delayed by true time delay, tau sub ij, multiplied by weights, W sub ij, and summed to form each of the N beams. Let me now summarize the current status of this project. We are at the juncture of the base period that ends in early August and the option that has received its first increment of funding. In the base effort, we accomplished several critical milestones. First, a new programmable delay element that was invented in phase 1 has been perfected by the regular integrated circuit development cycle of design, fabrication, test. The key element can be programmed to either produce a 1 clock period delay, which is 25 picosecond for 40 gigahertz clock frequency, or a few picosecond delay in the so-called JTL mode. Second, we have designed a new multiplier. Third, we have improved the digital decimation filter, or DDF. Last but not the least, we have optimized serial biasing of circuitry, which is the single most important hurdle that has prevented large-scale integrated circuit realization in superconductor microelectronics for the past 2 decades. This has also had a positive impact on a very different project on design tool development called Super Tools, sponsored by the Intelligence Advanced Research Project Agency, or IARPA. The IC fab is government furnished, and one of the challenges has been to accommodate the relatively long 6-month delay in chip fabrication. However, the quality of the chips are excellent, and we have been able to make steady progress and have completed the development of all 4 key components listed in the top right quadrant: serial biasing, programmable delay line, digital decimation filter, and the multiplier unit. We are collaborating with Columbia University on this project, and last year we applied for and obtained a no-cost extension. Finally, we have designed some new chips with multiple ADCs addressing the Navy's specific program needs at either end of the RF spectrum. Next, we list the salient features of our approach. First, the modular approach enables extension to forming multiple simultaneous beams and altering their spatial profiles. Digital copying does not suffer from loss of power or fidelity. Second, true time delay is frequency independent. Therefore, this technique works over a wide frequency span, from below 100 Hz to over 100 GHz. The high frequency digitization in higher Nyquist zones is a result of us sampling with very short 2 picosecond white pulses. Third, short digital clock period, which is 25 picosecond for 40 GHz clock frequency and shorter for higher clock frequencies, implies precise time delays and therefore accurate direction and location finding. We have demonstrated spatial resolution of a few millimeters already. Furthermore, there is scope for more advanced processing techniques to obtain finer resolutions. Fourth, our approach using optimized serial biasing technique has far-reaching consequences. Superconductor circuits are current biased. Large digital circuits, especially those that have uniform structure such as delay multiply blocks or digital filter slices, can be serially biased to cut down the total bias current. This helps reduce the main component of power consumption in cryo-cooled systems employing superconductor chips, that which comes from heat through DC bias lines that supply power to the chip. I could talk for hours on this topic, as it is crucial for the future of the whole field of superconductor large-scale integrated circuits. If any of you are interested in learning more, please contact me and I'd love to discuss further. Finally, the electronic reconfiguration can be done very fast. in a nanosecond. This and other technology components that we are developing through the SBIR program will eventually be incorporated in our ADR product line. The fifth generation will incorporate ICs with multiple analog to digital converters to enable digital RF beamforming. The first prototype has done this already with multiple single ADC ICs. The next one will feature multi-ADC ICs that were designed and fabricated during the base period of this project. The first prototype is expected to travel to other Navy facilities after testing at Newark. The fourth generation systems are currently integrated in land vehicles and were demonstrated in 19-inch equipment racks in airborne and maritime platforms in recent field exercises by the Army Program Office. We are also closely working with NAVAIR on making our ADR product more convenient for transport and operation. We have been primarily working with different government program office and laboratories. In the past, we have worked with a number of large and small companies in the defense and intelligence communities. We are especially interested in partnering with companies that augment our technology with hardware and software for real-time data analysis. The fact that our technology uses cryogenic and superconductor electronics should not deter any of you from interfacing yours with our ADRs. Since ADR has standard digital output interfaces from a commercial off-the-shelf FPGA that is part of our system. We have also developed a host of FPGA-based processors and recorders to facilitate handling digitized RF data. For example, we offer digitally channelized data with programmable center frequency and bandwidths so that you do not have to handle the entire 20 gigahertz instantaneous bandwidth that our ADCs produce. Some of our collaborators do like to operate on the full 20 gigahertz bandwidth or even wider with higher ADC sampling rates, albeit not in real time. We have developed high throughput continuous data recorders to facilitate such interactions. Finally, if you'd like to learn more about our technology, please contact our CEO, Dr. Buchanan, or myself. Thank you so much for your time.